Okay, kinematics and dynamics is our next topic, and those of you who do physics will have heard these things before, hopefully. Okay, so some definitions to start off with. Position, where an object is, where something is. So you might have a number line thingy here, for example, that's X metres. So the arrow there pointing at the positive direction, that might be 0, 20, 40, 60, 80, 100. And then you might have your thing here, and it might be there, and then it might be there, for example, and travelling in that travelling in that direction, the direction shown for with the arrows. So yeah, when it's at B, it's 20 metres from the thing. All right, displacement. Displacement is change in position. So displacement equals change in position, change in x, or x2 minus x1. Very Alright, so for example, let's draw a thing here, x metres. So 0, 20, 40, 60, 80, 100. And we might have this thing that's at the following position. So it might start here, then a couple of seconds later it might be there, then a couple of seconds later it might be here, and then a little bit of time later it might be there, and then might head back the other way. So it might be here, and then maybe there. So the journey that the thing's gone, it's gone down here, and then it's come back. I've gone a little bit too far with my coming back. Alright, so I travel in that direction and then come back in that direction. Call this S, A, B, C, D and E. Alright, so that's time equals 0, time equals 2, time equals 4 that's there, time equals 6 that's here, time equals 8, and time equals 10 that it's at E. Alright, so you can work out the displacement between any of those points should you wish to. So, for example, displacement from C to E. So our displacement x2 minus x1. So where it ended up minus where it started. So where it ended up is at E, which is here, and where it started was at C, which is there. So it ends up at 70 metres, but it started at 100. So 70 minus 100, maybe 30 metres from where it starts. And then got, say, look at displacement journey. So displacement equals, again, x2 minus x1. So where it finished up minus where it started. So I finished up at E, which is at 70 metres, and it started at S, which is 0 metres. Okay, that's different to distance. And so distance is the actual I'm going to use the word distance, which is bad. Anyway, the actual distance travelled. Okay, so the displacement's just how the distance between where it started and finished, but distance travelled. So if we want to know the distance for the journey, we need to look at the fact that it's travelled here up to there and it's come back. So when it travels from here up to there, it's travelled 100 metres and then it's come back 30 metres. So my actual distance travelled is 100 plus the 30 equals 130 metres. It's the actual distance travelled. Now what that brings us then to is velocity and speed. And often we talk in terms of average velocity, average speed, just since they may change. So the average velocity is our displacement over time, and our average speed equals our distance over the time. So if we're looking at our journey, our average velocity, the displacement, was 70 metres, and the time was 10, so it's 7 metres per second. Whereas our average speed, though, was the distance travelled, which is 130 over 10, which is 13 metres per second. Right, and the reason they're different is just from the definitions, displacement and speed. Alright, so what does this things look like then if we stick them on a graph? So if we stick it on a graph, time down here and position here, then anytime you have a straight line like that, so these sections here, this section here, constant velocity. This section here, section here, the flat one, that's still constant velocity, but it also a bit more constant. Zero velocity is what that one, particular one there looks like, I should say. Alright, so let's get on to an example. Okay, so let's have a look at page 515 in your text and example 2 that we're looking there. It says Luna Park has a new game called Hit the Duck. To win, you must knock down a mobile duck that moves backwards before it's in a straight line on a 5-metre track. You have 3 shots with small sandbags. The position time graph shows the position of the duck at various times t. Rightio, so there's our thing with our duck. Alright, so, and of course you can see that in page 515. So first question says, what's the initial position of the duck? So initial means time equals 0. There it is. So A, that's at 200 metres. How long did the game last? Well, you can see the movement of the duck by the red line, and it finishes up here at 10 seconds. So the game lasted 10 seconds. Displacement, final displacement of the duck from its starting position. So final displacement, final minus the initial position, so it's at 100 minus 200, so minus 100 metres was final displacement from its starting position. Right, times for which the velocity is positive, negative, 0. Okay, so that's referring to these 3 positions. And it really relates to the gradients. So, for part D, for positive, it's between t equals 0, 3 to t equals 5. 0, it's from t equals 5 to t equals 6. And negative, it's t equals 6 to t equals 10. Alright, it's a bit messy there, but anyway. Hence find the velocity of 3 time intervals. Okay, so for the first time interval, that's this one here. It's 5 seconds. Displacement, remember? Displacement is displacement not in time. So for the first one, this bit here, its displacement starts at 200, finishes at 400, so this displacement is 200 over 5, which is 40. For the bit in the middle, it's 0 metres per second. That's this bit here. And then finally, that last bit, so our displacement goes from there down to there, so it's a negative displacement from 400 down to 100. So our average velocity is minus 300 over 4. In this case, which ends up as negative 75 metres per second. Alright, so that's that. Alright, one more thing, and that is position as a function of time. So all that means is that we have our position written as an equation. So it might be something like this, for example. X equals a half of t minus 1 squared, where t is between 0 and, say, 5. Alright, so as you can see, that's all there's our time, there's our position. So this tells us what the position is at any time. And so from that you can work out where it is at any time, you can work out its displacement between two times, etc. You can draw a graph off of it if you want, and that particular graph of that particular one. Looks like so. So time equals 0, it's going to be here at a half. Time equals 1, it's there. And this is a parabola. 5 minus 4 is 5 minus 1, I should say, is 4. 4 squared, 16, and then it's up here at 8. So this particular one goes like that, and then you can answer any of the questions. Alright, so there's problem set number 1 there for you. It's exercise 15A questions.